SEA A2 Unit 2 Topic 5 is on transition metals. This section looks at the first series of transition metals from titanium to copper, including the properties of the metals and their compounds. Complexes, analytical tests, and the chemistry of vanadium will also be examined. Here are the definitions for this topic that you'll find in the SEA glossary. A transition metal is defined as an element which forms at least one stable ion with a partially filled d subshell. The transition metals are found in the middle of the periodic table. This block of elements is described as the D block. Just a quick recap from AS level. Remember that when we do electronic configurations, we fill the 4s subshell before the 3d subshell. Here is a list of the electronic configurations of the elements in the first row from scandium to zinc. There are two that you have to watch out for. The first one is chromium. In this case, one electron is promoted from the 4s subshell into the 3d to give a half-filled d subshell. And the second one is copper, where one of the electrons is promoted from the 4s subshell into the 3d subshell to give a filled 3d subshell. Just a quick recap on the electronic configuration of transition metal ions. Always remember that the transition metals will lose the 4s subshell electrons before they lose the 3d. The definition for a transition metal is it is defined as an element which forms at least one stable ion with a partially filled d subshell. If we look at scandium and zinc, they're not actually classed as transition metals. The reason is scandium only exists in the +3 oxidation state, and if you have a look, you can see it does not have a partially filled d subshell, and zinc only is observed in the +2 oxidation state, where it loses its 4s2 electrons, but it has a filled 3d subshell. The physical properties of transition metals include high melting points, high boiling points, high densities, they conduct electricity, heat, are malleable, ductile, and sonorous. They also have certain common chemical properties. They can have several different oxidation states, they're good catalysts, they form coloured compounds, and they form complexes with ligands. The common ions for the transition metals have been shown in this table together with their associated colours. It can be seen that the +2 oxidation state and the +3 oxidation states are the most common. The highest oxidation states are in compounds with oxygen or fluorine. Potassium permanganate is where manganese in the manganate has an oxidation state of +7, and potassium dichromate is where we have our chromium in the dichromate with an oxidation state of +6. If we look at vanadium, which we're going to study later in the topic, it has a variety of oxidation states from +2 to +5. And finally, don't forget, scandium has only one oxidation state, +3, and zinc at +2. Transition metals and their compounds are used as heterogeneous catalysts. The transition metals are usually in the solid state and reacting gases are passed over the heated catalyst. You can see in this slide a variety of uses for transition metal catalysts. Some we have already met before. For example, the Haber process, where we use iron as our catalyst. The contact process, where we use vanadium 5 oxide as a catalyst, and nickel in the hydrogenation of alkenes. There are two main types of catalysts that we met at AS level. Homogeneous catalysts, where the catalyst is in the same phase as the reactants, and heterogeneous catalysts, where the catalyst is in a different phase from the reactants. Heterogeneous catalysis involves the process of chemisorption. The first step is adsorption, and that's where catalysts make the bonds with the reactant molecules. This weakens and breaks the bonds in the reactant molecules, where they then can recombine to form the product which breaks away from the catalyst. Transition metal compounds are coloured. When white light passes through a solution containing transition metal ions, some of the wavelengths of visible light are absorbed, resulting in coloured compounds. The next part of this topic is on coloured transition metal complexes. Here are the associated definitions for this part of the topic. Let's look at how we write a transition metal complex. We have here hexa-aqua-copper complex, which is a very common transition metal complex. When we write our complex, we put it in square brackets. So we either have the transition metal atom or ion, and then we have the ligands. In this case, these are water ligands, and we have 6 water ligands. And ligands are ions or molecules with lone pairs of electrons which can form coordinate bonds. And then outside the brackets, we write the overall charge. In this case, water ligands are neutral, so the overall charge is that on the copper ion. Here is an example of another common complex. This complex is tetrachlorocuprate. Again, you have a copper 2+ ion, but our ligands are chloride ligands, and instead of having 6, we only have 4. We mentioned water and chloride as a ligand in the previous slide. A ligand which uses only one lone pair of electrons to form a coordinate bond with a central metal atom or ion is called a monodentate ligand. We also can see that ligands can have different charges. So for example, our water molecule is neutral, but our chloride ligand has a charge of -1. These pictures show what a complex looks like. On the left-hand side, we have our hexa-aqua-copper complex, where the oxygen atoms in the water molecule have a lone pair of electrons that form a coordinate bond with the central copper ion. And on the right-hand side, we have our tetrachlorocuprate, where the lone pair of electrons on the chloride ion form a coordinate bond with the copper ion in the center. You can see that both of these complexes have different charges, +2 for the hexa-aqua-copper and -2 for the tetrachlorocuprate. They also have different shapes, and we will talk about those shapes later on in the video. If we have a transition metal complex, we can find the oxidation number of the transition metal from the complex. So if we have a look at this complex, we have 5 neutral water molecules and 1 chloride ligand, which has a charge of -1. So if we start to do our calculation, if we have an overall charge of +1, then the cobalt must have a charge of +2. You might want to pause the video and try the example given below. And the answer for nickel is in the +2 oxidation state. Let's move on to bidentate ligands. Bidentate ligands are ligands which use 2 lone pairs of electrons to form 2 coordinate bonds with the central metal atom or ion in the complex. There are 2 common bidentate ligands that we need to be aware of. The first one is 1,2-dimenoethane, where you have a lone pair of electrons on each nitrogen. And the other example is the ethane dioate ion, which comes from ethane dioic acid, where you have a lone pair on each oxygen. These ligands can form 2 coordinate bonds to the transition metal ion. In both of these complexes, even though there are 3 ligands, each complex has 6 coordinate bonds. The next example we will look at is a polydentate ligand. And this is a ligand which uses many lone pairs of electrons to form more than 2 coordinate bonds. And the example that we need to know in this topic is EDTA. If you look at the structure, you can see 1, 2, 3, 4, 5, 6 lone pairs of electrons, which means EDTA can form 6 coordinate bonds to a central metal atom or ion in a complex. The 4- is the charge on the EDTA. It's important to remember that with polydentate ligands, it often appears that the coordination number of the complex is 1 or 3 because that is the number of ligands you use, when in fact the coordination number is 6 as normal. It is just that each ligand is bonded twice. Let's now look at some of the common shapes of transition metal complexes. The table on the slide shows the most common shapes, which tend to be either tetrahedral or octahedral. And you can see our hexa-aqua-copper complex that we met earlier is an octahedral shape, whereas our tetrachlorocuprate is tetrahedral. Here we have the most common shapes of the transition metal complexes. On the left we have an octahedral example, and on the right we have a tetrahedral example. If you're asked to draw these, it would be a good idea to show some three-dimensional structure. Water and ammonia form octahedral complexes, but on the right-hand side, you can see that the chloride ligands, which are larger, forms tetrahedral complexes. So the chloride ion is a bigger ion than the water molecule, so less chlorides can fit around the metal ion. Later on in the unit, we will meet a cancer treatment called cisplatin. This is a transition metal complex, but it is a square planar shape, and it has 2 chloride ligands and 2 ammonia ligands. The chloride and ammonia ligands can be either cis to each other or trans, hence the 2 different forms of the molecule, and it is the cisplatin that is used as the cancer treatment.